Hello, Math 1224. This is Dr. P with Lesson Launch 14.3 from Discrete to Continuous. So I promised in the last video that I would talk a little bit about what in the world all of this series stuff has to do with all the other theory and calculation that we've learned to do in the rest of the course. So that's what I'm going to try to accomplish here. I'm going to try and make a connection between this topic of series convergence and everything else we've done in the course. So just as a review, you'll remember in the last couple of videos we talked about the sum from k equals 1 to infinity of 1 over k times k plus 1. And we talked about how that's the sum of 1/2 plus 1/6 plus 1/12 plus 1/20, etc., etc. And we saw that that's the limit as n goes to infinity, excuse me, as n goes to infinity of the nth partial sum. And the nth partial sum was n over n plus 1, and the limit of that was equal to 1. So that's saying that the sum of all of these numbers is 1. All right? And we've also talked about, even though you may not realize it, we've also talked about series like this one, the sum from k equals 0 to infinity of 3 over 2 to the k. You actually know how to find the sum of that series. You may not realize it, but think about what this is. If we write out the first few terms, which is always a good strategy for thinking about these things, if you write out the first few terms, starting with the k equals 0 term, when k is 0, that's going to be a 1 down there. So I'm going to get 3 plus 3/2 plus 3/4 plus 3/8 plus etc. And that actually turns out as a geometric series. That's an infinite geometric series. If we want to find the nth partial sum of that, then we use the formula that we saw in the presentation last time by Dylan and Muhammad. That was, gosh, what was that anyway? The nth partial sum, which was equal to a plus ar squared plus etc. up to ar to the n minus 1. I believe that Dylan gave for that the formula a times 1 minus r to the n over 1 minus r, and that was the sum of the first n terms of the series. Sum of the first n terms. Okay? Now you might want to go back and review why that was the case, how we got to that point, because I feel like sometimes, just for my own peace of mind, rather than memorize a formula and risk getting this exponent wrong or something else wrong, I just figure anytime I see one of these, I can do the algebra that Muhammad and Dylan did in their presentation, and I can get to this point myself if I need to. But I'm not going to do that right now. I'm just going to use this formula for the nth partial sum and say, well, the limit as n goes to infinity of that 1 minus r to the n over 1 minus r, well, as n goes to infinity, this r to the n will go to 0, provided that the absolute value of r is less than 1. If absolute value of r is equal to or greater than 1, then this thing won't go away. If r is equal to 1, then actually this formula doesn't work anyway because that's undefined. And if r is negative 1, then this value bounces around as n increases. But in this case, if I look at this series that I started with up here, there we go. If I look at this series up here, I can think of that as a geometric series with a equals 3, the first term, and r equals 1/2. So if I look at what this converges to here, well, that converges to a times 1 over 1 minus r. That r to the n goes away there. And in this case, if a is 3 and r is 1/2, then that sum, the sum of the entire series, is going to be 3 over 1 minus 1/2, that is equal to 6. So all that to say that the sum of this infinite series is equal to 6. So we can actually find the sum of that infinite series as well. So what we have here is a couple of different examples of series, infinite series, whose sums we can calculate exactly. That's the good news. The bad news is that is not at all typical. Not at all. Most series that I write down, I may be able to figure out whether they converge or diverge if I'm lucky. But even if I can do that, even if the series converges and I can find some way to show that, I'm probably not going to be able to find the exact sum. So let me give an example here. Suppose I write down the series, the sum from n equals 1 to infinity of 1 over n to the p, where p is a constant, and let's say it's a positive real constant. I'm not going to say any more than that about it. Maybe it's an integer, maybe it's not an integer, it could be 1/2, it could be pi, we don't know. But let's say that we are looking at the sum from 1 to infinity of 1 over n to the p. That's a good example of a series for which typically I'm not going to be able to find the exact value using elementary methods. Actually, fun fact, this series is connected to an interesting problem in mathematics called the Riemann hypothesis. Now, I don't want to go too deep into this. I know that some people don't like when I go off on tangents. But the Riemann hypothesis has to do with this mysterious function zeta of p. And I don't even know if I don't even know if I've written the letter zeta correctly. I think that's it. But the Riemann hypothesis is concerned with this function zeta of p, which is actually defined to be the sum from n equals 1 to infinity of 1 over n to the p. So whatever value that has, I call that zeta of p. So I think of this entire sum here as something that depends on p. And there's a question about how that function behaves in the complex plane. I won't go any deeper into it than that. You can look it up on Wikipedia. There's a lot of people interested in it. In fact, there's a $1 million bounty on the solution right now. And a lot of very impressive mathematicians have thrown their energy at this. But anyway, we're just here to figure out, if I look at this series here, does this converge? And we have to realize that when we say that, the question of whether this converges or not is very likely to depend upon what the value of p is. Because if p is quite large, then the values of these terms are going to get small very fast. And by virtue of that happening, the sum of these terms might happen to converge. On the other hand, if p is something very small, then if it's still positive, then these terms are going to approach 0. But they might approach 0 at a very leisurely pace. And if that happens, then who knows? Maybe the sum of these terms goes off to infinity and maybe it converges to something finite. We will see. So the way I'm going to think about this problem is I'm first just going to write down, just going to explore this, investigate by writing down the first few terms. So the sum from n equals 1 to infinity of 1 over n to the p, that's equal to 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p plus 1 over 4 to the p, and so on. Now, in the meantime, I'm going to look at something else. I'm going to look at a function, a continuous function. That function is going to be f of x equals 1 over x to the p. And look at the graph of that thing in the coordinate plane. All right, so here's what a graph might look like. Now, I look at this and I notice that as x goes to 0, this thing's going to infinity. So I just want to make sure and get that in the graph accurately. And as x gets bigger, provided that p is positive, this is going to get smaller. So I think that my graph is going to look something like this. Asymptote there, and then another horizontal asymptote as we go off to infinity. And then how fast we go to infinity, that's going to depend upon p. So I'm just trying to draw sort of a general schematic here. And I'm going to put some tick marks here. 1, 2, 3, 4, and so on. Now, look at this sum here. One way that I could think of this sum, this infinite sum, is I could actually draw a picture of this sum in the coordinate plane. So just hang with me here for a second and see if you can follow this. So what if I draw this 1 over 1 to the p by drawing a rectangle here in the coordinate plane? I claim that that's a rectangle of area 1 over 1 to the p. Now, why would that be the case? Well, this point here, this side of this rectangle, this is f of 1. That's 1 over 1 to the p there. By the way, that's always going to be equal to 1, but I just want to refer to this in a way that's generally useful. And then the width of this box is 1 because it starts at 0, ends at 1. So I think the area of that box is 1 over 1 to the p. Now, what about 1 over 2 to the p? I'm going to draw a rectangle here. Now, let me make that a little bit more vertical there. There we go. should be entirely underneath this graph. Now you'll notice the y-coordinate of that point is 1 over 2 to the p, and this thing has a width of 1. 1 over 3 to the p, I'm going to draw as a rectangle here. 1 over 4 to the p, I'm going to draw as a rectangle here. And then I haven't written down the term 1 over 5 to the p, but I could draw that as well. And I could draw 1 over 6 to the p, and then after that I'm sort of out of picture here, but you can imagine the picture going on forever. So look at what I've done here. What I've done is I've basically thought of this, I'm thinking of this series, this infinite series, as a Riemann sum, like an unbounded Riemann sum, for this integral. For the integral from 0 to infinity of 1 over x to the p dx. Now there's a bit of a problem with that, because this integral is problematic in more than one way here. Notice that at 0, this function has a discontinuity. It's got an asymptote. So really, I'm going to instead think of this as a Riemann sum for this integral, and just sort of knock off this first rectangle here. I'm just going to think of the relationship between this part of the series and this integral here. Okay, so I don't know if there's some way for me to get rid of that one box. I'm just going to shade that in a different color and ask you to ignore it. I know that's a little bit tricky, but let's sort of forget about that for a minute. I'm going to move this over, and then I'm going to write down an inequality and see if I can convince you that this inequality is true. So here's what I think is true. I think that the sum 1 over 2 to the p plus 1 over 3 to the p and so on, all of that stuff, I'm excluding the first term, but I think all of that is less than or equal to the integral from 1 to infinity of dx over x to the p. Okay, now I promise you I'd try to convince you of this, so here's my argument. This sum here, the sum of all these terms, this is the sum of the areas of all these rectangles here, not including that first one that I sort of shaded off in purple. And this integral here, that's the area under the curve from this line all the way to infinity. So I think that's just an area argument there, that I can say the sum of this series is less than or equal to this integral here. All right. Now let me establish something else as well. Okay, so now let's see if I can get rid of that. Actually, you know what? I think I'm just going to start a new picture here, because I actually want to make a completely fresh argument. So now I'm going to try and represent this sum in a different way again. So this time I'm going to use the color green, still using the function f of x equals 1 over x to the p. That hasn't changed. Okay, same graph as before. That hasn't changed either. But this time I'm going to represent this series differently. So watch this. This time I'm going to represent 1 over 1 to the p like this. Let me put my tick marks down. Just a sec. There we go. 1, 2, 3, 4, 5, and so on. All right. So this time, here's my 1 over 1 to the p. Watch this. Oh, this is so cool. I always love doing this argument. That's 1 over 1 to the p, because now look, I've put my height of the box here. That's 1 over 1 to the p. That's f of 1, because it's on the graph and it's at x equals 1. And the width of that box, still 1. Now this box here, this is going to be, area of that box is 1 over 2 to the p. And then the area of this box here, oh, sorry, I sort of shaded that clumsily there. Let me see if I can get rid of that. Try that again. That's 1 over 3 to the p. And then I've got another box here, that's going to be 1 over 4 to the p. And just like last time, I could keep doing this forever. It won't all fit in the picture, but let's imagine it's all there. Now this time, I have all of the terms of my series here. I am actually going to keep them there. And I'm going to write this down. Based on this picture, I also think that the sum of this series, the entire series this time, that's going to be greater than or equal to the integral from 1 to infinity of dx over x to the p. So now I'm thinking of this series as a left-hand Riemann sum for this function. Up here, I was thinking of it as a right-hand Riemann sum, and each of these sort of led us to a certain inequality. So if we put all this together, oh man, you have no idea how excited I am about this. I don't think you could possibly know. All right, so based on these two inequalities, I think I can do the following thing. First of all, I can rewrite this one in the following way. I'm going to just add that 1 over 1 to the p in there. And that's going to be less than or equal to that integral, sorry, this is a little bit sloppy here, dx over x to the p, that whole integral plus 1. Now, why is that true? Well, I'm taking this inequality here, and I'm really just adding 1 to each side. On this side, I'm adding it as 1 over 1 to the p, and on the right side, I'm just adding it as 1. So I just took this inequality, added 1 to both sides. So what all of this means is that I know that this entire series is less than or equal to something, and it's also greater than or equal to something. So putting all that together, I think the sum, 1 over 1 to the p, plus 1 over 2 to the p, plus 1 over 3 to the p, etc., that is going to sit between the value of this integral, this improper integral, and the value of that improper integral plus 1. Sorry, I realize I'm saying it in the opposite order that I'm writing it, but I think it's going to sit in between those things. So for this inequality, I'm using this, and then for this inequality, I'm using this. All right, still with me? just barely, perhaps? Okay, let me get to the punchline then. Here's the punchline. If I'm interested in whether this sum converges or diverges, all I have to do is figure out whether this improper integral converges or diverges. If this integral, if this diverges, then ultimately the sum from n equals 1 to infinity of 1 over n to the p is greater. So it also diverges. Now again, why is that true? That's true because if I assume that this diverges, then, well, this is something that's even bigger. Something bigger than divergent is still divergent. But on the other hand, if that integral converges, then the sum from n equals 1 to infinity of 1 over n to the p is also going to converge. Now, why is that? That's because if I know that this is finite, if this has some finite value, well, adding 1 is still going to produce a finite value, and this is going to be less than or equal to that. So, in fact, I can say more than that this converges. I can say it converges to something less than or equal to this integral plus 1. So, what does all that mean? Now, I've been trying to make the videos so that the videos can be used independent of which Calc 2 class I'm teaching in the future. But I can't resist the opportunity here to use something that we know, because I think we know when it is that this integral converges or diverges, and that's by the MacLean conjecture, which is actually now the MacLean theorem because we proved it. And that was, if p is greater than 1, then that integral of 1 over x to the p, that converges. And if p is less than or equal to 1, then that integral diverges. Well, it turns out now, because of all this work that we've done here, it turns out that the very same thing is true for these series. So we could call this, I don't know, I guess I wrote this down, so I'm going to call this the Dr. P corollary. A corollary is just a statement which follows from a known theorem. The Dr. P corollary is that if P is greater than 1, then the sum from n equals 1 to infinity of 1 over n to the p, that converges. And if p is less than or equal to 1, then the sum from n equals 1 to infinity of 1 over n to the p diverges. Actually, this is not usually called the Dr. P corollary. It's actually called the Dr. P series test, because it's a way of testing whether a certain collection of series converges or diverges. But for some reason, it's gotten shortened over the years, and it's usually just called the P-series test. Anyway, there's one major idea that I want you to get out of this video, and it's actually not this P-series test. It's this idea of using integrals to determine whether a series converges or diverges. That's actually a very generalizable idea. So here's the idea. And then I promise I'll stop. This is like the longest video I've ever done. I appreciate your patience. This is kind of a compensation for me not being able to do any lecturing in class on Wednesday. So here's the major idea. Besides the P-series test, I mean, I want you to know the P-series test, but I actually am more interested in you understanding this major idea. So the major idea is, consider the sum from n equals 1 to infinity of f of n, where f is a continuous function that satisfies a few conditions. So first of all, it's continuous on 1 to infinity. It is always decreasing, that's important, and it's always positive. So if those three things are satisfied, then I know this. Then the sum of this infinite series has the same behavior either convergent or divergent. So it's either convergent with the following or divergent with the following, as the integral from 1 to infinity of f of x dx. In other words, if this converges, and if this diverges, then this diverges. The way we saw that here was we had the series, boy, this is a lot of work, my goodness, I apologize. We had the series sum of 1 over n to the p. We compared that to the continuous function 1 over x to the p, which we knew is always positive, always decreasing, and of course continuous. And we just thought about Riemann sums, infinite Riemann sums of this improper integral here, the improper integral from 1 to infinity of that function. And it turns out we can sandwich this series in between that improper integral and that improper integral plus whatever this first term was. That's the idea of the proof. And so we're going to do some examples of that in class. That was, holy moly, almost 25 minutes. In total, I think I've kept you for about 50 minutes, like the equivalent of an entire lecture. So I appreciate your patience, and I will not see you in class. Dr. Dueñas will, but I will see you on Monday when you can ask me more questions about this. Bye-bye.